Well, thank you for the invitation. I'm going to give you an overview on nanodiamond and thin diamond films for biomedical applications. I will tell you what they are, their properties, how they are applied in the biomedicine field. I will give you some of the examples, how we are using these diamond films, and then I will point out challenges and limitations of implementing this technology in biomedicine. I will finalize with some future perspectives. So, well, nanodiamonds are carbon-based nanoparticles that have this diamond-like structure. They contain sp3 hybridized carbon atoms arranged in a tetrahedral array, which gives the diamond and the nanodiamond this extreme hardness and chemical resistance. In the case of nanodiamond, we're talking about small-sized particles, 2 to 10 nanometers, generally below 100 nanometers in size. And then they contain nitrogen vacancy centers, which enables optical and magnetic sensitivity. Why should we use nanodiamonds for biomedical applications? Well, nanodiamonds have been shown to be biocompatible. It is easy to modify their surfaces to target different moieties. They have a stable fluorescence, and this makes them ideal for targeted drug delivery, bioimaging, and sensing. The key properties of nanodiamonds. So, as I mentioned, they are biocompatible and non-toxic for in vivo applications, or at least they show low toxicity, especially compared to other carbon-based nanomaterials like carbon nanotubes or graphene. They emit fluorescence without photobleaching due to these nitrogen vacancy centers, and they can be easily surface functionalized for attaching drugs, proteins, and other biomolecules. This gives them the following advantages. They have high stability in physiological environments. They are versatile. They can interact with various biological molecules, and they are easy to integrate in different biomedical systems like imaging systems in the clinic. Nanodiamonds have been used for drug delivery applications. Because of their high surface area and additional functional groups, it is effective. I mean, it is easy to attach drugs and targeting moieties to control drug release for targeted delivery into cells and tissues. Nanodiamonds have been used, for instance, to deliver doxorubicin, a chemotherapy drug, directly to tumors. They have also been used to attach and deliver nucleic acids with reduced degradation for gene delivery. The benefits are enhanced viability of the drug and reduced side effects when you are using this targeted delivery strategy. Concerning bioimaging and diagnostics, as I mentioned, nanodiamonds are fluorescent because of these nitrogen vacancy centers. And the fluorescence is bright and stable. It's resistant to photobleaching, and it's ideal for long-term imaging, even within the body. Among the applications for imaging include monitoring processes at the nanoscale within cells, diagnostic imaging for real-time tracking of biological molecules, and these NV centers, they contain these electrospin states. And this can be exploited for quantum sensing of temperature, pH, magnetic, electric fields, and pressure at the cellular level. This is within tissue, within cells, and even within organelles. This is an example of how we use these nanodiamond films for quantum sensing of biomolecules, in this case, microRNAs. So we have a surface here, the nanodiamond, and the NV centers are depicted here in red. Then we have in the solution manganese, a cation, and in the microRNA, which is negatively charged. So the manganese cations interact with the negatively charged microRNA, and this complex can absorb on the surface of the diamond. Now, when we applied green light, we can change the spin state of the NV centers, and then we change it to M0, and then let it thermally relax to ±1 level. During that relaxation, there will be a change. That's the panel in B, the graph B. During that relaxation, there will be a change in the fluorescence that is emitted by the NV center. Now, when there is magnetic noise on the surface, like here the case of this manganese and the DNA on the surface, that will affect the relaxation time. And then we can, by monitoring this relaxation, in this case it's T1 relaxation, so spin lattice relaxation, by monitoring these changes in relaxation time, we can monitor magnetic noise, and in this case, a molecule being attached on the surface. And this is exemplified here in graph C. So this is like a common experiment where we flush different solutions in a microfluidic device. So in section 1, we only have the surface in water. There is low contrast. As soon as we inject manganese, we increase magnetic noise, and at the same time, we increase contrast. When we introduce the microRNA and manganese, we increase further the contrast, and then when we inject a chelating agent like EDTA to remove the manganese, we bring the system back to basal levels. Now, we have been able to detect picomolar concentrations of the nucleic acids, and we're improving the surface to detect single molecules. In tissue engineering, nanodiamonds have been used to enhance scaffold strength and to support cell adhesion and growth, to encourage differentiation in bone and cartilage regeneration. Nanodiamond can be used to coat implants, and that offers antimicrobial properties to reduce infection risk and to improve durability and biocompatibility for long-term implants, especially those load-bearing implants. So the benefit is promotes healing and reduce inflammation in implantable devices. This is another example how we use surface wave plasma chemical vapor deposition to coat three-dimensional objects. These are like acetabular shells, like in C, you see before coating and after coating these micrographs. And then we have tested growing cells with different functionalization, oxygenation, hydrogenation, and different topographies. By tuning this topography and determination, we can control cell growth, like favor osteoblast growth over fibroblast growth. So what are the challenges? Well, one is manufacturing and scalability. So we need consistent production with uniform properties of the nanodiamonds. Biocompatibility and safety is still an issue. We don't have long-term toxicity studies. And we don't know about stability and accumulation in the body over long exposure times. Then there is a high production cost that hinders large scale implementation. So the future perspectives are to improve the synthesis to make it scalable. And, well, and then we have these potential applications in biomedicine. We can use it for real-time diagnostics down to single molecule level, neurotherapeutics, theragnostics, and implementation in multifunctional devices for imaging and therapy. And yep, with that, I would like to thank you. And I think I'm back here.